This is Unit 4, Video 5. In this video, we will talk about special types of double replacement reactions, and there will be two categories of these. So let's get to it. The first category we'll mention is an acid-base neutralization reaction, and this involves an acid. Now, an acid is a compound beginning with the element H, and hydrogen is the active part of an acid. A base is a compound ending with hydroxide, OH. That's the active part of a base. When you put a base and an acid together, what you get is salt and water for the products. Now, what you can see is this is a simple double replacement reaction. The hydrogen comes in and replaces the sodium comes in and replaces the hydrogen. You get yourself sodium chloride for the product, and then hydrogen OH, HOH, which is H2O. So you can readily see this just from the perspective of a double replacement reaction, but now we're calling this an acid-base neutralization reaction. And you can perform a little demonstration if you use indicators, and you can see that an acid with a base will form a neutral solution, and that's why it is green here, denoting neutrality. The second type of reaction is the formation of a precipitate. Now, a precipitate is a solid that falls out of a solution or forms from solution. So an example of this would be you have two solutions here that are mixed, and they form this white cloudy solid. Eventually this white cloudy solid precipitates to the bottom, and you have a little layer of an insoluble solid. The precipitate could be white. The precipitate could also be other colors, yellow, orange, sometimes even black. And from the perspective of a double replacement reaction, silver comes in and replaces sodium. Sodium comes in and replaces silver. So again, you get yourself silver chloride and sodium nitrate. Now, the precipitate is the one that will be solid. Only one of these two products will end up being a solid, and that is going to be the precipitate. We will talk about how to determine that the precipitate is actually this compound and not this compound through solubility rules. Okay, let's define electrolytes and non-electrolytes, and this is referring to solutions. An electrolyte, when dissolved, dissociates, which means breaks apart in solution to make ions, and then it conducts electricity. A famous example is salt. Because salt is made of ions, sodium chloride, it will conduct electricity. So here is salt dissociating, breaking apart into sodium ion and chloride ion. Non-electrolytes, on the other hand, when dissolved, do not dissociate. And since they don't dissociate, they will not conduct electricity. And that's why we call these electrolytes, because of them conducting or not conducting electricity. A famous example of a non-electrolyte is sugar. Sugar here dissolves. Everyone knows that sugar is soluble in water, but it does not conduct electricity. So it goes simply from a solid to an aqueous. But it does not dissociate like the salt did. Now, when ionic compounds dissolve, they separate. This is what happens. So this is a little more of a detailed explanation of how this happens. So ionic compounds, most ionic compounds will be electrolytes, whereas molecular compounds, also known as covalent compounds, remember these are two or more nonmetals, whereas ionic compounds, we define them as a metal and a nonmetal. As a quick review. So if you have an ionic compound made of a metal and a nonmetal, it will dissociate and conduct electricity. If you have two nonmetals, the covalent compounds do not dissociate. However, there are exceptions. The major exception to this are acids. Acids are technically covalent compounds because they have hydrogen, a nonmetal, and chlorine, another nonmetal. However, acids behave slightly like an ionic compound in that the acid separates, actually dissociates. The hydrogen falls apart from the chloride, and the hydrogen is what makes the acid acidic, technically. So if you remember, we said that hydrogen kind of acts like a metal. And it is placed sometimes, or oftentimes, on the periodic table with the alkali metals for that reason. You also have bases, which are going to be rare for us, called molecular bases. So here, NH3 is a famous molecular base. It will also conduct electricity when dissolved in water. So in the same category as molecular acids. And here is the experiment to determine if something is an electrolyte. You simply pour the solution in a beaker and then pass a current through the beaker to see if, or through the solution to see if that current makes it from one electrode to the other electrode. Here they're actually using graphite pencil leads for this reason. Graphite is actually conductive, conducts electricity, and then depending on how bright this is, tells you how much of an electrolyte it is. Okay, it turns out you could be a strong or a weak electrolyte. So the strong electrolytes dissociate completely, and since they dissociate completely, we'll use a single arrow when writing a strong electrolyte. So, for example, hydrochloric acid, the famous strong acid, will dissociate completely, and it turns out to be a strong electrolyte. Weak electrolytes, on the other hand, dissociate only partially, and for that we'll use a double arrow, like here. An example of this is acetic acid. This is acetic acid, which also dissociates, but not completely, which means most of the acid actually appears in solution in this form. Very little of the acid appears in the dissociated form, in the broken apart form, and that's why it's a weak electrolyte. This applies almost exclusively to acids. They can also apply to molecular bases, as we've seen, but this idea of strong versus weak electrolytes, and technically weak electrolytes, can be acids. That's really the only category for us where we'll encounter weak electrolytes. Here is a picture of what we just discussed. So acetic acid, here is the formula of it again, is very soluble in water. In other words, it dissolves if you throw it into water. However, it dissociates only about 1%. So just 1% of the acid will break apart. Whereas hydrochloric acid is very soluble as well, but dissociates completely, close to 100%, 99.999%. And so what you see here is an example of a strong acid. Here is the hydrochloric acid. It's a bit tough to see, but every one of these molecules has a red atom, we'll say that's the chlorine, and a white atom, that's the hydrogen. So each of these is HCl. Notice that when they fall into water, each one of them breaks apart. So all the white and the red are apart. And that's why a strong acid conducts electricity very well, because you're full of ions. You make a solution that's full of ions. A weak electrolyte, on the other hand, has the acid coming out, and when it hits the water, most of the molecules actually stay together. Notice these stay together. They have not dissociated. They have not broken apart. Some have, but most of the acid will stay together, and that's kind of the idea. And depending on how much of it dissociates determines how weak that electrolyte is. So a weak acid is where the acid stays together and a few of the ions break apart. Strong electrolytes then are the strong acids. Now, there are 7 strong acids that you must know of, 7 strong acids, and those are hydrochloric acid, hydrobromic acid, hydroiodic acid. These are the 3 binary acids, and they're actually in group 17, from group 17, from the halogens. Notice fluorine does not appear in here, which means hydrofluoric acid is a weak acid. Hydrofluoric acid is not strong. And then you have 4 oxyacids: nitric acid, sulfuric acid, chloric, and perchloric acid. So the 7 strong acids are strong electrolytes. Remember, a strong acid completely separates. That's why it's a strong electrolyte. All your strong bases are strong electrolytes. Now, strong bases are hydroxides, metal hydroxides. So group 1 and 2 metal hydroxides are strong bases, and technically you can think of these as ionic compounds because you have yourself a metal and a non-metal. It's just that the non-metal is a base. So now here it says that beryllium hydroxide and magnesium hydroxide are not included in this list, even though it's a group 2 hydroxide, because they're just not very soluble. But when they are soluble, they're strong bases. That's the idea. And then ionic compounds, if they're soluble, and we'll talk about solubility rules in the next lesson, will be strong electrolytes. So technically, all ionic compounds are electrolytes because they break apart into ions, because they contain ions, and that's what you need to conduct electricity. So if an ionic compound dissolves, it will break apart, and that's kind of the idea. So this looks like a lot, but really what we're saying is strong acids are strong electrolytes, strong bases are strong electrolytes, and ionic compounds are strong electrolytes. That's really what we're saying here. It's just a list of them. Weak electrolytes then contain weak acids and weak bases. So the weak acids that are not part of the strong acid list, so most of the acids out there, thousands of acids, are actually weak. You only have 7 of the strong. And then there are thousands of weak bases out there called molecular bases. And they're nitrogen-containing bases usually, the non-hydroxide bases, non-metal hydroxide bases. They are weak electrolytes. And then your non-electrolytes are actually your molecular compounds or your covalent compounds, other than acids and bases, because remember, acids and bases can also be considered molecular. So this is an example of something called solvation. Solvation, I know the preacher talks about salvation. This is a little different. Solvation is actually the dissolving of something by water. So water molecules here are coming in and dissolving this substance here. And this is a covalent substance, a molecular substance. Notice they just simply dissolve it, but it does not dissociate, it does not break apart. Water molecules don't break it apart. Whereas if you take an ionic compound, this is ionic, this was covalent. The ionic compound actually does dissociate. The water molecules, as they're solvating it, will separate the negative and separate the positive. And as they solvate it, they'll essentially surround the negative. The positive side of the hydrogen orients itself to the negative side of the anion, and the negative side of the oxygen orients itself to the positive cation in the salt. This is like table salt that dissociates, and that's why this conducts electricity. This is just a visual picture of what is happening. Okay, let's do an example problem, and then we'll wrap up. So here it says classify each of the following aqueous solutions as a strong electrolyte, weak electrolyte, or a non-electrolyte. So this first example, magnesium chloride, we recognize is an ionic compound. Now anything that's ionic will have ions, will be a strong electrolyte because it will dissociate. So this is a strong electrolyte. In fact, every ionic compound is a strong electrolyte. So do you see any other ionic compounds? Here is another ionic compound. Cobalt sulfate or cobalt 2 sulfate is also a strong electrolyte because it is ionic. Now down here, KOH, potassium hydroxide, is also a strong electrolyte. You can think of it as ionic, but it's not only ionic, but it's also a base. It's actually a metal base. And it's a metal base because of the hydroxide, because of the OH. So technically it's ionic, therefore it's a strong electrolyte. Alright, we see covalent compounds. The C2H6 is a covalent compound. In fact, all the rest of them are covalent. Oxygen is obviously covalent. Covalent, remember, you have 2 or more nonmetals. Now, oxygen here is diatomic, so you technically have 2 atoms that are nonmetallic. And this is covalent. But however, this covalent compound is actually an acid. And this being an acid allows it to be a weak electrolyte. So if you're covalent and if you're not an acid, you're a non-electrolyte. In this case, both of these are non-electrolytes. Whereas if you're an acid, you have to ask yourself, is this a strong or a weak acid? So strong or weak. And because we have ourselves a weak acid, it's not one of the 7 strong acids. This is actually hypobromous acid. Hydrobromic acid would be strong. This is actually one of the strong acids. But hypobromous is a weak acid, which means it is the weak electrolyte. And this is the only weak electrolyte on the list. So again, ionic compounds are strong electrolytes. Covalent compounds are non-electrolytes, unless they are acids, which makes them weak electrolytes, if they are a weak acid. Hopefully that made sense. This wraps up then the video for us.